to all of you. Myself, I am the Dr. Chenna Reddy, Associate Professor in AC Department in Kesava Reddy Engineering College. Okay. So today, in the subject of digital logic design, we are going to study that. So why we need to go for a digital logical design. The important thing is why exactly we need to go is the importance of the digital system is. One is called as the accuracy and speed and power consumption and the size. So these are the four important characteristics. So why we need to go for the digital systems. The first one is called as the accuracy. So we all know that accuracy is nothing but the system which can able to read the right value. So nowadays it's very important for us. So system should be more accurate. So when it is accurate, so without any error, so which can able to read the values. Such a character which we can understand or we can study in case of the digital system. That is, it should be a more accurate system. So it should be more accurate system. Right? This is the first part. And next case is the speed. Right? So speed is nothing but it is a response of the system. So how fast it can read the value, how fast it can perform the operation. So that depends upon the character which is called as the speed. So speed of all the digital system is very high. So high speed digital systems are there in our digital logic design. Right? And next one is the power consumption. So power is very important. All the systems which can able to be performs the very less energy. So less energy and more work should be there in case of any systems. So that's what. So which can consume the very less energy in performing of the operation. And third one is the size. So size is it takes very less space in the integrated circuit to be perform the operation. Right? So in integrated circuit, it should take the very less space so that the integrated circuit which can able to be perform the many operations. So that the size is very important the parameter in case of the digital circuits. So these are all the four important the characteristics which is observed in case of the digital system. So because of their advantages, these systems which are become more popular in nowadays. So nowadays you can see that a watch is a digital watch, a television is a digital, a mobile phone is a digital, and a digital panel, whatever we can see the display systems, all are the digital systems only. So because of these characteristics, so these systems are become more and more popular. So what is the behind of the digital system is? So first part in the digital system, we need to understand about the logical gates. Right? So what is logic? Word anytime logic. Logic means easy to understand. That is called as logic. We used to call it. Logic means the system which has a two possible way of understanding. One is 0 or 1. So that is the system which can able to be performed with the help of a binary. So binary means 2. So there is only a 2 possible values which we can see in any type of the logical gates. And this is also being represented with on and off. So 0 is off and 1 will be treated as on. Or other we can also represent no or yes. Or we can also represent open or close. So this is a very understanding terms in case of any logical gates. And coming gate. Why we used to call it gate? Gate is called like control. Gate is nothing but which can control the logical operations. The operation like gate will be very understanding term which is called as open and close. Open or we can also call as closed. Okay. So that is what we need to be understanding of any logical gates. And these logical gates which can able to be perform the logical operations. Logical operations. All logical gates will be perform the logical operations. What is logical operations? The logical operations in the digital systems are basically it will be three. One is called as the AND operation, OR operation, and the inversion operation. Or we used to call it as the NOT operation, NOT. We used to call it NOT operation. These are very important, the basic operations under the logical gates. Now we will see that individually how it is going to be utilized for making of the logical operations. But if you see this, this AND which is going to make the multiplication. Multiplication will be performed by the AND gate, and OR will be performed the addition, and NOT will be performed the inversion. So as we are using these three, we can create any logical operation. That is what very important in case of combining of these three basic operations, and we can create any type of the logical operations. Now coming to the multiplication, when you call it as multiplication, you represent it with the dot. The dot in case of any expression that represents the multiplication, right? And next addition, which is very similar, like plus sign will be used for making of addition operation. And NOT, we used to be create some complement dash. So y dash, x dash, r dash, based on the variable which we are using at the input. So in that we can make the inversion operation. Now I can show with some examples. So examples of the multiplication use taking of the 2 or 3 variables, right? So in the first case I can take the 2 variables which are a and b. So I can write a Boolean expression which is y is equal to, y is called as the output expression for any logical gate, which is represented by the y is equal to a dot b. So a and b are variables, so we can multiply like a dot b, right? And next one is 3 input. If you want to go with the 3 input, you can represent like a dot b dot c. Like that you can go for the any inputs, right? So this is what I shown basic, like a 2 input and 3 inputs. Now I can take some table, right? Truth table. We used to call as a truth table. The table which is going to make us understanding the operation of that logical gate. Like when you take 2 inputs, so a and b will be the inputs, and y will be the output, which is called as a dot b. And here, as it is a 2 inputs, so how many combinations we get? 2 power n. So n is called as variables, 2 inputs, 2 power 2, which is going to get the 4 combinations. 4 combination output. We used to be represented like 0, 0, 0, 1, 1, 0, and 1. So now we build the multiplication operation with using of these variables. 0 dot 0 will give the 0. 0 dot 1 will also give the 0. 1 dot 0 will give the 0. Only in case of 1 and 1, that is 1 dot 1 will is going to give the 1. So that is about exact the truth table of the AND gate, right? Like that you can also create for a 3 input or the 4 input also. So this is what the exact we can understand the truth table of the AND gate, right? So this is called as multiplication. Similarly, I can also make to study plus b. And if you want to make it as a 3 input, you can also make like a plus b plus and c. This is a 3 input expression. And now we will see that how we can make use the truth table of the R gate. So R which performs the addition operation, and I am going to make now the truth table. It is a table where we can understand the functioning of the logical gates. Such a table we used to be called as the truth table. Truth means what? Perfect, exact what we are going to get. That what we are going to study in the help of the truth table. So now for an R gate, when I want to make use with a 2 input. 2 inputs we already know that A and B are the inputs, and Y is your output, which is represented as A plus B. Now I already told that in case of the AND operation, as you are 2 inputs A and B, you are going to get the 4 combinations like 0 0, 0 1, 1 0 and 1 1. Now for this we need to create the output values, which is 0 plus 0 will be always 0, 0 plus 1 will be 1, 1 plus 0 will be 1, 1 plus 1 is 1. It's not 1 0, it will be the 1 0. So this is about, see that when you are seeing the truth table of the R gate, so one of the input is high, always its output will be high. That is about the logic under the R gate. When you see this AND operation, one of input is low, always your output will be low. Unless if 2 inputs are high, then only the output is high. This is the logic under the AND operation. Right? So similarly, when you compare with AND and OR, you can see that the truth tables. So how it is going to create the output values. So here in this case, if one of input is high, its output will be always high. If the one of input is low, here output will be always low. So that is the important logic what we are going to be studying in case of the R gate. Now I can show the 3 input. When you take a 3 input R gate, I can show with the 3 input R gate. So when 3 input R gate, you can take the variables like A, B, C. Not only A, B, C, you can also take the like values like X, Y, Z. It may be different. Your variables may be different, but you can take like A, B, C or X, Y, Z, or if you want to take any other variables, you can also be used. But when you are taking this, so like we have the A, B, C as a 3 input. So 3 input means how many combinations we are going to get. So as it is a 3, this is a 3 is a variable. 2 power 3, we are going to get the 8 combinations. 8 combinations we are going to say. We are going to inform now these combinations with the expressions A plus B plus C. You can see this, how we are going to make to be form the truth table of the So 0 as it is a combination, we have the first case will be 0 0, then 0 0 1, then 0 1 0, then 0 1 1, then 1 0 0, then 1 0 1, then 1 1 0, and then last one will be 1 1 1. All inputs. Initial will be all zeros, and final will be all the variables values will be 1. Now we are going to inform. We'll see that. So as it is all 3 inputs are 0, so your output will be 0 because 0 plus 0 plus 0 will be 0. So if one of input is high, its output will be always high. Here one of input is high, so output will be high. 1 plus 1 is also in case that it is 1. So again input is 1, 1, again 1, again 1 plus 1 is there 1. Again all 3 inputs are 1, output is 1. So what you understand from this is, see one of input is very high, this output is always high in case of the R gate. Right? So these are what logical operations we need to understand with the help of the truth tables of the logical gates. Now the third we are going third basic gate, which is called as the NOT gate. NOT. What is NOT? What is NOT? So NOT is called as the inverter. So we used to represent small NVT inverter or complement. We used to be called as complement. So what is complement? This gate we have only one input and one output. It's not similar like AND gate or OR gate. It is only one input and one output. One. Now I can see this. One input means I can draw the schematic of the NOT gate. The schematic of NOT gate is very similar of our PN junction diode, but it's not a PN junction diode. It looks like very similar to the PN junction diode. Right? This is a schematic of the NOT gate. The schematic of the NOT gate, which has one input and only the one output. So A is input and Y is equal to, we can represent it as A dash. Now coming to the truth table. So as it is a one variable, we used to get only the two possible values in case of the truth table. That is A is a variable and Y is equal to A complement. So its complement is what? Inversion. Inversion is equal to 1. The two possible values, one is 0 and other is 1. So 0, if you give the input as 0, you are going to get 0 bar, which should be equal to 1. If you give the input is 1 and you are going to get the output is 0, because 1 bar is equal to 0 in case of the distance. Now similarly, I want to show you that about the schematic of the OR gate also. Two input schematic of the OR gate. Right? Schematic of the OR gate. So when you see that two input schematic of the OR gate, so take the two variables like A and B, and it should be connected to the OR gate, and this is the schematic of the OR gate. So this is what we need to draw. This is a symbol of the OR gate where Y is equal to A plus B. If you want to draw, you want to make the three. You can also make the three inputs by taking off three variables like A, B, and C, which is being connected to the OR gate. Should be connected to the OR gate, and we can create the Boolean expression which Y is equal to A plus B plus C. So like that, you can make the n number input for any OR gate or the AND gate. This is a schematic. Now I can also show the logical operation for the logical operation schematic of the AND gate. What is the schematic of the AND gate? The schematic of the AND gate, I can show this as a two input schematic of the AND gate. This is A and B, and Y, which is equal to A dot B. And three input, the schematic of the is Y is equal to A dot B dot C. So these are all schematics. Exactly, we need to understand, because all the simplifications and manipulations and all this will be done only with the help of the schematics. It is going to recognize that which gate we are using. That's what we are going to help us in the design of the all logical circuits. So these are all the basic operations. Now we are going to exactly study about the universal gates. It's a very important gates, because universal gates are very important gates, because any logical operation we can be able to be created by using the universal gates. So these are our basic gates, and the second gate we are going to study about the universal gates. Universal gates. What is universal means? The meaning of universal is a gate which can able to be perform any logical operations. Like using of this universal gate, you can create AND operation, you can create NOT operation, you can create the NOT operation, you can create the XOR operation, you can create the XOR operation. Like apart from this, if we have any other logical operations in the digital system, all that can also will be created with the help of the universal gates. What are universal gates? The first universal gate is the NAND gate. NAND gate. And the second is the NOT. These are very important gates in the digital electronics. Right? What NAND? NAND is nothing but what you can easily understand, and NOT and AND. By the combination of NOT and AND, you can create the NOT and AND. By combining of these both, you can create the NAND. Similarly, if you want to create the NOR operation, you can create by using the NOT and the OR. So you can create the NOR operation. Very similar. Unless knowing of these two basic gates, you cannot understand what is the logical operation of the NAND or the NOR. So for that, it is need to study the basic operations of the logical gates. Now I can show the schematic of the NAND gate, schematic of the NAND. So I can take the 2 input schematic first. We can go for the 3 input also, like 4 input, whatever you like. So first let me go with the 2 input NOT gate, NAND gate. So NAND it's like very similar of AND, but in output we used to make the bubble. The bubbling is very important. The bubbling which makes the complement, right? The bubbling which can make the complement, so that we can have the 2 inputs here, A and B, and we can write the output is A into B whole bar. Right? So now we see the truth table. What is the exact truth table of the NAND gate? So here again we have the 2 inputs, A and B are the inputs, and the Y is the output. Y is equal to A, B whole complement. We see that as it's the 2 inputs, how many combinations we get? We used to get the 4 combinations: 0, 0, 0, 1, 1, 0, and the 1, 1. So like this 4 common combinations which we are going to see for all the truth table where it is a 2 input logical gate. So now we see that 0, 0. So 0 into 0 will be 0, 0 complement will be 1. This is a 1 logic. And 0 into 1 will be 0, 0 bar will be 1. Again 1 you are going to get here. This is also 1. 1 into 0 is also a 0. So 0 bar will be equal to 1. Last case 1, 1. A is 1 and B is 1. So that 1 into 1 will be 1. 1 complement will be 0. So one thing we need to understand here. Why I used to call why logical operations are too easy when compared with the all other circumstances. See that inputs values are in form of binary and output value is also in the form of the binary. So that's what we need to make easy to understand all the logical operations, right? So here especially you can see that it is two opposite of the AND gate. This truth table is two opposite of the AND gate. In AND gate we have seen that in the last case when the 2 inputs are high, then only the output will be high. But where in case of the NAND operation, you are going to see that if 2 inputs are high, your output will be 0. Right? You can see the first operation 0, 0, you are going to get 1, and 0, 1, you are going to get 1, 1, 0, you are going to get 1, and 1, 1, you are going to get the 1. That is, if one of the input is low in case of the NAND gate, its output will be always is equal to 1. That's what the functioning of the NAND gate. Right? So this is what is schematic. This is a very important schematic in case of the universal gates. Similarly, we need to study the NOR operation also. NOR. These are two gates which are going to play the major role in the digital electronics. Unless with these gates there is no digital circuits. Nowadays you can see that in designing of all digital electronics, once you open the circuit or chip, you can, most of cases you are going to see these two gates. Because what is need of basic gate is, because without the basic gates there is no NAND gate and NOR gate. Unless of knowing that you can't understand the NAND operation or the NOR operation. So because of that it is need to study the basic gates. So now coming this NOR gate, you can see the schematic. The schematic is like a OR gate, but in output we are going to connect with the power. So this is going to be the NOR operation. So here we can write that the output Boolean expression. All the output expressions we used to be represented under the Boolean only, because that is a term which we are using in the digital electronics. So Boolean expression. Then normally we used to call in regular equations, but in logical circuits the output expressions always we need to call as the Boolean, because that is a word we need to always use in case of the writing of the expressions. That is A plus B whole complement. This is what the expression of the NOR operation. Now we go with the truth table, because unless creating of truth table, we may not understand the exact operation of the logical gates, right? So here again we have the A and B are the inputs, and we have the Y is the output, where we can represent A plus B whole complement, right? So now as we know that as it has two variables, so we can take four combinations 0 0, 0 1 and 1 0 and 1 1, right? It's a four combination. Now we build the output value, what is the exact operation of the NOR gate. Now 0 plus 0 will be 0, 0 bar will be equal to 1. So when you making addition, but they have the complement, whole complement is there. So 0 plus 0 will be 0, 0 bar will becomes the 1, because bar represents the total value will be inverted. So 0 becomes 1 and 1 becomes the 0. So next case students, you can see this 0 and 1 is there here. A is 0 and B is 1. You can see this value. So that 0 plus 1 is 1 and 1 bar will becomes the 0. Again the third case, A is 1 and B is 0. So in this case A plus 0 will be 1 plus 0 will be 1 and 1 bar becomes the 0. And last case, two inputs, two variables, A is 1 and B is 1. So A plus 1 plus 1 will be 1 and 1 bar becomes the 0. So now what you need to study, you need to understand what is the exact logical operation of the NOR gate. You can see that if one of the input is high, its output will be always low. Unless if two inputs are high, then only the output will be high in case of the NOR gate. Right? Now you can see, you can compare between the NAND and the NOR operation, because these two gates which are universal gates and these two gates which are helping us to create any logical operation in the digital electronics. So we need to give more importance for these two gates. So unless knowing of this, it is very difficult to understand the coming logical operations under the digital electronics. So this is what I need to share with you, that this is very important the type of gates in the digital electronics. Right? So The next we are going to study about the special gates under the digital electronics. The special gates we have after the universal gates we have the special gates. The first one is called as the XNOR gate, XNOR gate, and the second one is the XOR gate, XOR. Right? XNOR and the XOR. These are the special logical gates under the digital electronics. Right? So first let me go with the XOR and then we go with the XNOR, right? XNOR, right? So now I'm going to build the X is nothing but what? X is called as exclusive NOR you already know that what is the exact NOR, right? Exclusive NOR, right? And this is called as exclusive OR, which is called as exclusive OR gate, right? Now you can see the students what is the exact difference of these two special gates. Here we have XNOR and here we have the XOR. Right? So what is XOR and what is the XNOR? Right? So the difference is, students, I can show the first case what is the XNOR. XNOR, right? So XNOR is what we can take the two input XNOR. XNOR, okay. So two input what XNOR is what as taking of two variables A and B. Here XNOR gate representation is very similar of the OR gate, and there is exclusive line which should be connected to the symbolic of the NOR gate. NOR gate take the output and forward. This is called as you can see the Y. Here Y is equal to, we can represent the exclusive OR is what here A, B, exclusive A, exclusive B. A, exclusive B. What is A, exclusive B? A is exclusive B. What is the two input XOR gate, XNOR gate? So as it is two variables A and B, this is a schematic of the XNOR, and we are going to write the Boolean expression which is Y is equal to A XNOR B. This is a representing for the XNOR. XNOR when you want to represent under the digital, so you need to represent with dot and should be a circle, so that we can expand this expression which is AB plus A complement B complement. So this is what the exact Boolean expression for the exclusive NOR gate. So now I built the truth table for this because truth table is very important table in the formation of the any logical operation. So here A and B again, we need to take A and B. So when you take A and B, so we are going to get four combination, that is AB plus A complement B complement, right? So now we see that how we are going to build the output values for this combination of the inputs. Now you can see the students, inputs are low. Okay, 0 is what low, 1 is what high in case of the digital systems. This is what we need to understand from the digital language. 0, 0. So you can see the 0, 0 here, student. 0, 0. A is 0 and B is 0. This will be 0. And A is 0. 0 bar will be 1. B bar will be B is 0 and B bar is also 1. So 1 into 1 will be 1. 0 plus 1 will be equal to 1. Right? Second case, I can explain the second case. this value will be low. A is equal to AB plus A complement B complement. So in this case, one of input is low. So 0 into 1 will be equal to 0. Then A is 0, 0 bar will be 1, but B is 1. 1 bar will be 0. So 0 into something will be 0. So 0 plus 0 will be equal to 0. So that value is equal to 0. So here also opposite, so that you can write it directly, it is also 0. And last case we can check, students. So when two inputs are high, 1 into 1 will be 1. Again 1, A is 1 and B is 1. 1 bar will be 0. Again 1 bar will be 0. 0 into 0 will be 0. 1 plus 0 will be 1. So that the last case will be 1. So you can see the two tables. So when two inputs are same, A is same and B is same, so then only your output will be high, and remaining case the output will be very low. So this is a special gate under the logical operation, right? So now here you can see the y is equal to AB plus A complement B complement, and we have built the output values for the combination of the inputs. Now similarly, we can also study the second special gate operation, which is the second one, which is called as the XOR, right? Now we go with the two input XOR gate, similar to that of the XNOR. When A and B will be the inputs, A and B will be the inputs. These are inputs, and we have built the OR. It is very similar, but we are not connecting to the bubble at the output. So because it's OR gate, and this will be the exclusive, right? Exclusive. There will be a curve which is drawn before the basic OR gate. So now we are going to make the output expression where y is equal to A complement B plus A B complement. So this is called as XOR operation, for a two input XOR operation, and this simply we can also make to write like A XOR B. This is what in between the two variables plus and should be circled. So that represents the exclusive OR gate, right? Now coming to the truth table, when we go with the truth table once again for the XOR gate, as you are taking the two inputs A and B, and y will be the output. Here I can write the expression which is A bar B plus A B bar. This is what the output expression. Now we will make the inputs 0, 0, 0, 1 and 1, 0 and 1. So first case we will start. First case, what is happening is two inputs will be 0. So what is happening anyway? In this case, B is 0. Other side A will be 0. 0 into something will be always 0. Again, this side also one of the variable is 0. 0 plus 0 will be 0. And finally, two inputs are low. The outputs will be low. This is what it is. Second case. Now, second case I am going to study with the A is 0 and B is 1. So in this case, as 0 complement becomes the, I can write the expression here, A complement B plus A B complement. Now I can make the expression. Now I will go with the second case, A is 0 and B is 1. So A complement is become 0 complement becomes 1 and B is 1 here, A dot B. That is 1 dot 1 plus A is 0, 0 into something will be always 0. So 1 into 1 will be 1, again plus 0, so which is equal to 1 plus 0 is equal to 1, and so that the output will be 1. So now opposite both will be opposite, this case is also 1. And last case, from this logical I understood that when two inputs are same, the outputs will be same. That is, first case we got 0, 0, and final case we are also going to get the same logic which is same. Right? So this is what the truth table of the XR gate. From this gate, it is very clearly you can understand the logical operation of the XR gate. Now we can compare. You can compare the both the special gates, XNOR and the XOR. What is difference in this schematic? What is difference in the output expression? And what is the exact difference in the truth table? So when you will see the first case, when 0 0, here also 0 0, but here it is 1, but this case it is 0. Right? Here the second case, if A is 0 and B is 0, this combination, for the XNOR gate, you are going to get the output is 0. But where in case of the XR gate, for this combination, you are going to get the output is 1. Third case, you can see that A is 1 and B is 0, your output is 0. But here in this case, A is 1 and B is 0, for this case you got the output is 1. And last case, when both inputs are high, the XNOR gate output is equal to 1. But where in case of the XOR gate, the output is equal to 0. So that is the difference what we need to understand from these two special gates. So these are the special gates under the logical gates, right? So with this we are studying the three important logical operations under the digital electronics or the digital systems. So with this, I am going to close the today session, and tomorrow we are going to study the designing of the logical operations. With this, thank you students, and thank you so much.